50 kilometers above Venus, the temperature drops to a comfortable 70 degrees. The atmospheric pressure matches sea level on Earth. You could almost breathe the air if it were not 96% carbon dioxide. Scientists have proposed building floating cities here, drifting through eternal golden clouds where humans could live in shirt-sleeve environments. The concept sounds impossibly elegant. NASA has studied it. Engineers have designed it. Physicists have calculated it. On paper, Venus cloud habitation works perfectly. But something terrifying happens when you look closer. Every brilliant solution to living on Venus creates problems more devastating than the ones it solves. The closer we examine these proposals, the faster they collapse. This is why humanity's most promising off-world home might be the most dangerous trap in our solar system. If you enjoy having your assumptions shattered and your mind expanded, hit that like button and subscribe. We're about to explore why the most elegant idea in space colonization falls apart the moment you actually try to build it. Now, get yourself comfortable. Let's begin. Picture yourself standing on a platform floating 50 kilometers above a world of fire. Below you, hidden beneath layers of golden cloud, lies the most hostile surface in our solar system. Temperatures exceeding 860 degrees Fahrenheit, hot enough to glow visibly red in darkness. Pressure equivalent to being 900 meters beneath Earth's oceans. Acid rain falling through air thick enough to drown in. But up here, at this precise altitude, something remarkable happens. The temperature drops to a comfortable 72 degrees Fahrenheit. The atmospheric pressure matches sea level on Earth almost exactly. The sunlight streaming through the clouds provides more energy than anywhere on Earth's surface. You could step outside in nothing more than an oxygen mask and a light chemical suit. Welcome to the cloud cities of Venus, the most elegant solution to off-world habitation ever conceived, and the most devastating trap in our solar system. The physics of this idea seems almost too perfect to be true. At 50 kilometers altitude, the Venusian atmosphere reaches a density where breathable air becomes a lifting gas. Nitrogen and oxygen, the mixture humans breathe, is lighter than the carbon dioxide surrounding it. A balloon filled with ordinary Earth atmosphere would float naturally at this altitude without any heating or complex machinery. You could build a habitat that lifts itself simply by being pressurized with the air its occupants need to survive. Think about what this means for engineering. Every other space habitat in human history has fought against physics to keep its occupants alive. The International Space Station requires constant attitude adjustments, regular reboosts, and complex thermal management systems. Lunar habitats would need to resist the vacuum of space while shielding against radiation and temperature extremes, spanning hundreds of degrees between sunlight and shadow. Mars' surface installations must maintain pressure against an atmosphere so thin it might as well not exist. But a Venus cloud habitat would float passively, held aloft by the same air its crew breathes, requiring no energy expenditure simply to stay in place. Compare this to every other off-world colonization proposal humanity has seriously considered. Mars requires pressurized habitats fighting against near-vacuum conditions, where a single hull breach means instant death. Lunar colonies need radiation shielding against the unfiltered solar wind that would give unprotected astronauts lethal doses within hours. Orbital stations demand constant maintenance of complex life support systems that recycle every drop of water and every molecule of oxygen. But Venus cloud habitation offers something no other destination provides, an environment where the physics actively helps rather than hinders human survival. The numbers are remarkable when you examine them closely. At 50 kilometers altitude, atmospheric pressure measures approximately 1 bar, virtually identical to Earth's sea level. Temperature averages around 75 degrees Fahrenheit, comfortable for humans without any heating or cooling. The dense carbon dioxide atmosphere blocks most cosmic radiation, providing shielding comparable to Earth's magnetic field. Gravity at this altitude measures approximately 8.87 meters per second squared, roughly 90% of Earth normal. These conditions exist nowhere else in the solar system, outside of Earth itself. Scientists first proposed this concept in the 1960s, when Soviet probes began revealing just how hostile the Venusian surface truly was. Early astronomers had imagined Venus as a tropical paradise hidden beneath its thick clouds. Science fiction writers populated the planet with swamps, jungles, and alien civilizations thriving under perpetual overcast skies. The reality was far worse than anyone predicted. Surface temperatures averaging 864 degrees Fahrenheit, sufficient to soften aluminum and destroy any electronics within seconds. Atmospheric pressure 92 times greater than Earth, equivalent to the crushing depths found only in Earth's deepest submarine trenches. An atmosphere composed almost entirely of carbon dioxide with clouds of concentrated sulfuric acid. No probe humanity has sent has survived more than approximately 2 hours on that surface. The Soviet Venera program revealed these conditions through a series of increasingly robust landing attempts throughout the 1970s. Venera 7 became the first spacecraft to successfully transmit data from another planet's surface in 1970, returning signals for approximately 23 minutes after touchdown before succumbing to the environment. Later missions achieved survival times approaching 2 hours through increasingly robust thermal protection. Later missions extended survival times through ever more elaborate thermal protection, but none lasted more than about 2 hours. The Venusian surface destroys everything humanity has ever sent there with brutal efficiency. But those same missions revealed something unexpected. The hostile conditions existed primarily at lower altitudes. As altitude increased, temperature and pressure decreased dramatically. At 30 kilometers, conditions were still lethal but less immediately so. At 40 kilometers, temperatures dropped to levels merely uncomfortable rather than instantly fatal. At 50 kilometers, the numbers suddenly matched Earth. This discovery launched decades of scientific papers exploring whether humans could live not on Venus but in Venus, floating through its upper atmosphere in structures ranging from simple balloons to massive aerostats the size of cities. The concept gained serious scientific attention because it solved problems that plague every other colonization proposal. Consider the challenge of radiation exposure. On Mars, the thin atmosphere provides minimal shielding against cosmic rays and solar particle events. Astronauts on the Martian surface would accumulate radiation doses significantly higher than safety limits allow for extended missions. The Moon offers no atmospheric protection whatsoever. But Venus's dense atmosphere absorbs radiation so effectively that cloud-level exposure rates fall below what astronauts experience aboard the International Space Station. The planet's atmosphere provides natural radiation protection that would require tons of shielding material to replicate artificially. Consider the challenge of structural integrity. Habitats in vacuum or near-vacuum environments must withstand tremendous pressure differentials between breathable interior atmosphere and the void outside. A single micrometeorite impact or structural failure can cause explosive decompression. But at Venus cloud altitude, internal and external pressures balance almost perfectly. A hull breach would cause gradual air mixing rather than explosive decompression. Occupants would have time to locate and repair damage rather than facing instant catastrophe. The failure modes become manageable rather than immediately lethal. NASA studied the concept seriously in 2015 through a project called HAVOC, the High Altitude Venus Operational Concept. Engineers designed inflatable habitats that would float at 50 kilometers, powered by solar panels and housing crews of 2 astronauts for 30-day missions. The designs included realistic mass calculations accounting for every system component. Trajectory analyses demonstrated feasible flight paths from Earth. Mission architectures specified deployment sequences, operational procedures, and return profiles. On paper, everything worked. The physics was sound, the engineering was achievable. The concept passed every preliminary review that NASA's rigorous assessment process could apply. The HAVOC team calculated that their proposed airship could measure approximately 130 meters long, roughly the length of a Boeing 747 aircraft. This envelope would contain enough volume of breathable atmosphere to provide significant lifting force while housing a crew gondola, solar power systems, and scientific equipment. The habitat would enter the Venusian atmosphere at high speed, deploy its envelope during descent, and achieve neutral buoyancy at approximately 50 kilometers altitude. The entire deployment sequence was designed using proven aerospace technologies adapted for Venus conditions. The appeal extends beyond mere survival physics. Venus offers strategic advantages that no other destination matches. It is the closest planet to Earth, approaching within approximately 38 million kilometers during inferior conjunction, compared to Mars's minimum distance of approximately 55 million kilometers. This proximity translates directly into lower mission energy requirements. During optimal launch windows, reaching Venus orbit requires less propellant than reaching Mars orbit. The energy savings compound when considering round-trip missions that must carry return fuel or generate it at the destination. Communication delays between Earth and Venus measure only 4 to 24 minutes depending on orbital positions, compared to the 4 to 24-minute delays for Mars. This might seem comparable, but Venus missions would typically operate near the shorter end of this range, while Mars missions often operate near the longer end. More importantly, Venus's proximity means rescue missions could reach stranded explorers faster than any other interplanetary destination. If something goes wrong at Mars, help is at minimum 7 months away. At Venus, relief could arrive in as little as 4 months during favorable alignments. Solar energy availability at Venus exceeds anything possible at Mars or beyond. Venus orbits closer to the Sun, receiving approximately twice the solar energy per square meter that Earth receives. At cloud-top altitudes, solar panels would generate more electricity than anywhere on Earth's surface. This abundant energy could power life support systems, scientific equipment, communications, and potentially industrial processes for resource extraction. The energy budget for Venus operations looks remarkably favorable compared to the constant power struggles that would plague Mars surface installations. Venus also matches Earth in size and mass more closely than any other planet in our solar system. Venus's diameter measures approximately 95% of Earth's diameter. Its mass equals approximately 81% of Earth's mass. Surface gravity consequently measures 90% of Earth normal, close enough that long-term physiological adaptation might prove unnecessary. Astronauts on Venus would experience weight nearly identical to what they feel on Earth, avoiding the bone density loss and muscle atrophy that plague long-duration missions in reduced gravity environments. The atmospheric density at 50 kilometers provides enough pressure to eliminate the need for complex pressure suits during external activities. Astronauts could perform maintenance or scientific observations wearing only chemical protection and breathing apparatus. Compare this to the bulky, movement-restricting spacesuits required for any activity outside pressure vessels in vacuum environments. The freedom of movement possible at Venus cloud altitude exceeds what any other off-world destination could offer. Temperature regulation requires minimal energy compared to the extreme heating or cooling needed elsewhere in the solar system. Mars' surface temperatures range from minus 125 degrees Celsius to plus 20 degrees Celsius, requiring substantial heating for any habitat. Lunar temperatures swing between plus 127 degrees Celsius in sunlight and minus 173 degrees Celsius in shadow. But Venus cloud temperatures remain comfortably consistent, requiring only modest climate control to maintain habitable conditions. Every factor that makes space colonization difficult seems to become easier at Venus cloud altitude. The engineering solutions proposed over decades demonstrate remarkable creativity from the aerospace community. Early concepts imagined simple balloon habitats, spherical envelopes filled with breathable atmosphere, and suspended beneath the cloud layer like weather balloons on Earth. These minimalist designs could theoretically be deployed with existing launch vehicle capacity, requiring no revolutionary new technologies. A simple balloon filled with Earth-normal air would float at Venus in the same way a helium balloon floats in Earth's atmosphere. Later proposals evolved into massive aerostats, football field-sized structures that could house dozens of inhabitants in rotating shifts. These concepts incorporated rigid internal frameworks for structural support multiple pressure compartments for redundancy, and distributed systems to prevent single points of failure. Some designs featured rotating sections to provide artificial gravity for sleeping quarters, allowing crews to maintain Earth-normal physiology during rest periods while experiencing Venus gravity during working hours. The most ambitious concepts described cloud cities kilometers across, interconnected networks of floating platforms supporting permanent populations of thousands. These visions imagined industrial facilities processing atmospheric resources, agricultural domes growing food crops, transportation systems linking distant platforms, and all the infrastructure of a self-sustaining civilization floating eternally through golden clouds. Science fiction artists rendered these concepts in stunning detail, capturing imaginations across generations. Structural engineers calculated that the buoyancy provided by breathable air would support substantial mass at minimal energy cost. A spherical envelope 100 meters in diameter would generate approximately 540,000 kilograms of lifting force at 50 kilometers altitude in the Venusian atmosphere. This enormous lift capacity could support substantial payload mass, including structural framework, life support systems, scientific equipment, consumables, and crew with margin to spare. Unlike orbital stations requiring constant attitude control and periodic reboosts, cloud habitats would float passively, maintained at altitude by simple physics requiring no ongoing energy expenditure. Unlike surface installations requiring heavy construction equipment transported at enormous cost, cloud structures could be assembled from lightweight materials and inflated upon arrival. The habitat essentially deploys itself, using atmospheric pressure to achieve structural rigidity. This eliminates the need for construction machinery, foundation preparation, or any of the civil engineering challenges that would complicate surface installations on any planetary body. The logistics appeared simpler than any alternative off-world destination by substantial margins. Scientists also noted that Venus's upper atmosphere contains all the chemical building blocks for sustainable habitation with impressive abundance. Carbon dioxide, comprising 96% of the atmosphere, could be processed into oxygen for breathing and carbon for structural materials. The carbon could form graphite, carbon fiber, or potentially even diamond under the right processing conditions. Sulfuric acid droplets pervading the cloud layer could theoretically be neutralized and converted into industrial chemicals, including sulfur compounds useful for various manufacturing processes. Water vapor exists in trace quantities throughout the atmosphere, approximately 30 parts per million at cloud altitudes. While this concentration seems trivially small, the enormous volume of atmosphere accessible to a mobile platform represents a substantial total water resource. Nitrogen for breathable air mixtures is present at approximately 3.5% concentration, sufficient for extraction. A self-sustaining colony might eventually manufacture everything it needed from atmospheric resources alone, achieving true independence from Earth supply chains. The scientific community treated these proposals seriously because the fundamental physics is genuinely sound. The numbers work when you check them. The calculations produce feasible results. The concept passes every preliminary engineering review that standard aerospace assessment methodologies apply. This is not science fiction speculation conjured by dreamers unfamiliar with engineering constraints. This is legitimate aerospace engineering published in peer-reviewed journals and studied by space agencies around the world. The Cloud City concept represents one of the most thoroughly analyzed off-world habitation proposals in the history of astronautics. Researchers from institutions including NASA, the European Space Agency, various universities, and private aerospace companies have contributed to this analysis over more than 5 decades. Thousands of pages of technical documentation explore every aspect of Venus atmospheric habitation. Conference papers, journal articles, doctoral dissertations, and official agency reports accumulate into a substantial body of literature. The concept has been examined, challenged, refined, and examined again by some of the most capable engineers and scientists in the field. But here is where the dream begins to crack. Every analysis that proclaimed cloud habitation viable focused on the same limited set of parameters: temperature, pressure, radiation, gravity, solar energy. These factors determine whether human survival is physically possible at a given location. They are the first-order constraints that any habitation proposal must satisfy. They do not determine whether survival is practically achievable over operational timescales measured in years rather than days. And Venus hides a chemical assassin in its clouds that destroys the fundamental assumption underlying every floating habitat proposal ever conceived. Sulfuric acid pervades the Venusian atmosphere from roughly 45 to 70 kilometers altitude. These are not trace amounts, detectable only with sensitive instruments requiring careful calibration. The cloud layer consists primarily of concentrated sulfuric acid droplets ranging from 75 to 98% concentration by mass. For comparison, laboratory-grade industrial acid measures only 93 to 98% concentration. Battery acid that can dissolve metal and cause severe chemical burns on contact typically measures only 30 to 50% concentration. The clouds of Venus are literally made of battery acid at concentrations that would dissolve most materials on contact almost instantly. This acid does not fall as occasional rain that might be avoided or sheltered against through careful mission planning. It exists as a persistent aerosol suspended throughout the exact altitude range where temperature and pressure become survivable for humans. The acid droplets range from approximately half a micrometer to several micrometers in diameter, small enough to remain suspended indefinitely in the dense atmosphere. They pervade the entire cloud layer in concentrations measured in hundreds of particles per cubic centimeter. You cannot see through them, you cannot avoid them, you cannot shelter from them. The region that makes Venus habitation theoretically possible is the same region most thoroughly saturated with corrosive chemicals. You cannot separate the favorable conditions from the corrosive environment. They occupy the same space because they result from the same atmospheric chemistry. Material scientists began quantifying this problem in the 1980s as more detailed atmospheric data became available from Soviet Venera probes and American Pioneer Venus missions. Soviet scientists in particular gained direct experience with Venus atmospheric chemistry through their aggressive landing program. The results were devastating for cloud habitation proposals. Common aerospace materials degrade rapidly under exposure to the acid concentrations, pervading the cloud layer at rates incompatible with long-term habitation. Aluminum, the workhorse metal of spacecraft construction prized for its favorable strength-to-weight ratio, corrodes into aluminum sulfate powder within weeks of continuous exposure to concentrated sulfuric acid at Venus cloud temperatures. The reaction proceeds steadily, consuming metal and producing expanding volumes of corrosion product that stress adjacent structures. Steel dissolves even faster through similar chemical processes. Titanium resists longer than aluminum or steel but eventually succumbs, its protective oxide layer undermined by persistent acid attack. Even specialized corrosion-resistant alloys developed for chemical processing industries. Alloys designed specifically to handle sulfuric acid in industrial applications show measurable degradation over timescales shorter than any reasonable mission duration for human habitation. The problem extends beyond metal structures to every component of a floating habitat. Balloon envelopes require flexible materials that can maintain pressure while remaining lightweight and durable enough to survive launch stresses and deployment. The corrosive aerosols attack most polymers commonly used in aerospace applications through various degradation mechanisms. Nylon, often used for high-strength fabric applications, degrades through hydrolysis accelerated by acid catalysis. Polyester weakens as acid breaks polymer chains. Polyurethane coatings blister and peel. Even specialized fluoropolymers like PTFE, better known by the brand name Teflon, face challenges when combined acid exposure, ultraviolet radiation, and mechanical stress operate simultaneously over extended periods. More critically, these materials cannot be fabricated into the large, flexible structures that balloon envelopes require while maintaining the precise properties needed for Venus operations. No known flexible material combines acid resistance, UV stability, mechanical strength, and manufacturability at the scales cloud habitats demand. The chemistry is relentless and inescapable. Sulfuric acid attacks materials through multiple mechanisms, including direct chemical reaction, catalyzed hydrolysis, and electrochemical corrosion in the presence of moisture. Different materials fail through different pathways, but all materials fail eventually. The concentrated acid finds weaknesses in every defensive strategy engineers have conceived. Protective coatings crack and delaminate. Sealed enclosures develop microscopic leaks. Corrosion-resistant alloys succumb at joints and welds, where metallurgical properties differ from base material. Researchers explored potential solutions throughout the following decades, with increasing desperation as the scope of the problem became clear. Perhaps acid-resistant coatings could protect structural elements from direct chemical attack. Perhaps continuous maintenance could replace degraded components before failure cascaded into catastrophe. Perhaps materials yet to be developed through advanced research might resist corrosion entirely. Each proposed solution created new problems worse than the original challenge it addressed. Coatings require perfect application, with no gaps, scratches, pinholes, or weak points where acid can penetrate to attack underlying materials. Manufacturing processes that work well in clean laboratory environments struggle to achieve perfection across large surface areas under field conditions. Any imperfection, however microscopic, creates a corrosion initiation site where acid concentrates and attacks the vulnerable substrate material. Once corrosion begins beneath a coating, it spreads beneath the protective layer, causing sudden catastrophic failure rather than the gradual predictable degradation that might be monitored and managed. Coatings also add mass that reduces the buoyancy margins, making floating habitats viable in the first place. And coatings themselves degrade under persistent acid exposure, requiring replacement over timescales comparable to the structural materials they protect. The coating becomes another component, requiring maintenance rather than a solution eliminating maintenance needs. Continuous maintenance demands spare parts, tools, replacement materials, and human attention that must be transported from Earth at enormous cost. Replacing degraded components before they fail requires manufacturing capability that itself requires equipment and materials subject to the same corrosion problems affecting primary structures. Machine tools corrode. Electronic components fail as acid vapor penetrates sealed enclosures. Diagnostic instruments lose calibration as their sensors degrade. A self-sustaining maintenance cycle proves impossible when the maintenance equipment degrades as fast as the structures it maintains. You cannot fix corrosion damage with tools that are themselves corroding. Novel materials represent the most hopeful potential solution, but decades of intensive research have failed to identify any practical candidate for Venus cloud applications. Materials that resist the cloud layer chemistry tend to be heavy, rigid, expensive, or impossible to manufacture anywhere except specialized facilities on Earth. Ceramics resist chemical attack admirably, but cannot form flexible balloon envelopes and shatter under the dynamic loads of launch and atmospheric deployment. Exotic nickel-based superalloys cost thousands of dollars per kilogram before considering the additional expense of launching that mass to another planet. Glass-based materials offer excellent chemical resistance, but fail catastrophically under mechanical stress. Every material that solves the corrosion problem creates other engineering problems equally severe. The mathematics of degradation rates versus mission duration tells a brutal story that advocates of cloud habitation have struggled to refute. Current aerospace materials would require replacement or significant structural repair within 6 to 18 months of continuous exposure to Venusian atmospheric conditions at cloud altitudes. Robotic missions lasting weeks or months might tolerate this degradation, accepting that equipment will fail but achieving objectives before failure occurs. Human habitation requiring years or decades of structural integrity to justify the enormous investment cannot proceed under these constraints. The gap between survivable duration and sustainable habitation spans orders of magnitude that no known material can bridge. Even the most optimistic projections from researchers genuinely enthusiastic about Venus exploration acknowledge this fundamental limit. NASA's HAVOC study, despite its thorough engineering analysis and genuine effort to demonstrate mission feasibility, proposed missions lasting only 30 days, precisely because longer durations would require solving the materials problem that no one has solved despite decades of effort. The study did not claim permanent habitation was achievable with current or near-term technology. It claimed that short visits might be possible if materials degradation could be managed through strict mission duration limits. This is not a ringing endorsement of Cloud City viability. It is an acknowledgement that the dream cannot become reality without breakthroughs that remain stubbornly out of reach. The corrosion problem affects every system required for habitat operation, not merely structural materials that might be over-engineered for extra margin. Electronics require protection from acid vapor that penetrates seemingly sealed enclosures through microscopic gaps in joints, seals, and cable penetrations. Integrated circuits corrode, solder joints fail, connectors degrade. The computing systems required for life support, navigation, communication, and scientific operations face the same chemical assault, threatening the structures housing them. Solar panels degrade as acid etches their surfaces, reducing power generation efficiency over time. The transparent covers protecting photovoltaic cells cloud and pit. Electrical connections corrode. Even the mounting hardware holding panels in position weakens. A habitat that starts with adequate power margins finds those margins shrinking week by week as its energy systems degrade faster than its power requirements decrease. Sensors used for navigation and atmospheric monitoring fail as corrosion attacks their delicate measuring elements. Pressure sensors lose calibration as their diaphragms corrode. Temperature sensors fail as their thermocouples degrade. Chemical sensors designed to monitor atmospheric conditions ironically succumb to those same atmospheric conditions. The instruments needed to monitor habitat health become unreliable precisely when accurate monitoring becomes most critical. Some researchers propose descending below the acid cloud layer to altitudes where sulfuric acid concentrations decrease substantially. This strategy accepts reduced lifting force from thinner atmosphere in exchange for reduced chemical attack. But below 45 kilometers, temperatures rise rapidly towards surface conditions that no material can survive for extended periods. The thermal gradient on Venus is brutally steep. The zone between corrosive acid clouds above and lethal heat below narrows to a thin band where conditions are merely awful rather than immediately fatal. This twilight zone provides no viable habitat location, only a slightly slower path to the same failure that defeats cloud-level operations. Others suggested ascending above the cloud layer to altitudes where acid aerosols disperse into negligible concentrations. This approach accepts reduced atmospheric density in exchange for reduced chemical hazard. But above 70 kilometers, atmospheric pressure drops to levels requiring full pressure suits for any external activity, eliminating one of the key advantages that made cloud habitation attractive. The buoyancy that makes floating habitats elegant disappears as atmospheric density decreases, requiring active propulsion to maintain altitude. Solar ultraviolet radiation increases to levels requiring heavy shielding that adds mass and complexity. The advantages that made cloud habitation attractive vanish as you climb away from the corrosive zone toward conditions resembling space itself. The chemical environment of Venus does not merely challenge engineering solutions through problems that might yield to clever design. It fundamentally negates the premise underlying every cloud habitation proposal seriously advanced. The hospitable altitude band exists only where corrosive conditions make long-term habitation impossible by any known technology. The physics that makes survival theoretically possible operates in the same atmospheric layer as the chemistry that makes survival practically impossible. You cannot have one without the other because both result from the same planetary conditions that created Venus as we find it. This realization forces a complete reconceptualization of Venus habitation approaches. If stationary floating habitats cannot survive long enough for permanent presence, perhaps mobile platforms that minimize exposure time by continuously moving through the atmosphere might work. If corrosion destroys everything eventually regardless of engineering countermeasures, perhaps robotic systems that can be replaced at acceptable cost might establish infrastructure before human arrival. If the acid cloud layer defeats all known materials through chemical attack, perhaps avoiding prolonged exposure entirely through different mission architectures might succeed where permanent presence fails. Each alternative approach seems to offer solutions to the corrosion problem that defeats stationary cloud cities. Each creates new categories of failure waiting to be discovered by anyone willing to look closely enough. The obvious response to the corrosion problem is simple: keep moving. If sulfuric acid destroys any structure that remains stationary in the cloud layer, perhaps a mobile platform that continuously travels through the atmosphere could minimize exposure while sampling different conditions. Perhaps the answer to Venus habitation is not floating cities, but floating ships, vessels that sail through the clouds rather than anchoring in them. This concept has attracted serious scientific attention precisely because it seems to solve the materials degradation problem that defeats stationary habitats through an elegantly different approach. The intuition behind mobile platforms draws from terrestrial experience with hostile environments. Ships at sea survive storms by maneuvering rather than anchoring. Aircraft avoid dangerous weather by changing course. Submarines evade detection by remaining in constant motion. The principle seems transferable to Venus. A platform that never stays in one place might avoid the worst conditions that would destroy a stationary structure. Movement becomes a survival strategy rather than mere transportation. Mobile platforms offer several theoretical advantages over fixed-position aerostats that make the concept worth examining seriously. By varying altitude, a moving vessel could spend time above the most corrosive cloud layers while descending into the temperate zone only when necessary for specific operations. The acid concentration varies with altitude, peaking in certain bands while diminishing in others. A platform capable of vertical maneuvering could theoretically minimize its time in the most chemically aggressive regions. By traveling horizontally, mobile platforms could exploit wind patterns that distribute acid concentrations unevenly across latitude and longitude. Venus atmospheric chemistry varies with location due to photochemical processes driven by solar radiation. Equatorial regions experience different conditions than polar latitudes. Dayside chemistry differs from nightside chemistry during the planet's slow rotation. A platform capable of navigating to favorable regions might extend its operational lifetime by avoiding the worst concentrations. By maintaining constant motion, mobile platforms could potentially prevent the accumulation of corrosive deposits that accelerate degradation in stationary structures. Acid droplets settling on surfaces concentrate over time, creating localized attack zones where degradation proceeds faster than general atmospheric exposure would cause. A moving platform might shed these accumulations through aerodynamic forces, maintaining a fresher surface condition than a stationary structure could achieve. The atmospheric dynamics of Venus actually encourage this mobile approach in ways that seem almost designed for aerial navigation. The upper atmosphere rotates around the planet once every 4 Earth days, driven by powerful winds that exceed 300 kilometers per hour at cloud-top altitudes. This phenomenon, called superrotation, moves the entire upper atmosphere around the planet 60 times faster than the planet itself rotates. The mechanism driving this superrotation remains incompletely understood, but its existence is confirmed by decades of observation. Lower atmospheric layers move more slowly than the upper atmosphere, creating vertical wind shear patterns that vary predictably with altitude. A mobile platform could theoretically exploit these differential velocities for propulsion and navigation. By ascending into faster-moving air layers, a platform could travel rapidly around the planet. By descending into slower layers, it could effectively slow its ground relative motion or even travel backward relative to the surface. The atmosphere itself becomes a transportation medium rather than merely a suspension medium. This wind-riding capability suggests that a mobile platform could circumnavigate Venus continuously, riding the atmospheric circulation like a sailing ship riding ocean currents, requiring minimal energy for horizontal travel. The superrotation provides free transportation around the planet. Vertical maneuvering between wind layers provides navigation capability. The combination seems to offer mobility without the enormous energy costs that would otherwise make continuous motion impossible. Solar-powered aircraft designs proposed by various researchers leverage this atmospheric circulation for propulsion while harvesting abundant solar energy for systems operation. During Venus's extremely long solar day, lasting approximately 117 Earth days, solar panels oriented toward the Sun could generate continuous power for propulsion, station keeping, and life support systems. The slow rotation means that a platform flying with the super-rotating atmosphere would experience continuous daylight for extended periods, simplifying power management compared to rapidly cycling day-night conditions. The same dense atmosphere that creates buoyancy for floating habitats also provides lift for aircraft wings, enabling flight at lower speeds than would be required on Earth. Atmospheric density at 50 kilometers altitude equals Earth sea level density, making conventional aerodynamic designs potentially viable without exotic modifications. Wings sized for terrestrial aircraft could generate similar lift forces. Propellers designed for Earth atmosphere would produce comparable thrust. The aerodynamic engineering translates almost directly from proven terrestrial experience. This atmospheric density advantage means that aircraft designed for Venus cloud operations could fly at surprisingly low speeds while maintaining altitude. Stall speeds would be comparable to terrestrial aircraft of similar wing loading. Control authority would remain effective at velocities that would cause Earth aircraft to fall from the sky. The forgiving flight characteristics might enable aircraft designs optimized for endurance rather than speed, maximizing the time available for scientific operations or survival between maintenance events. Scientists have proposed hybrid designs combining buoyancy and aerodynamic lift to exploit advantages of both approaches simultaneously. An airship with wings could float at safe altitude during periods of intense acid exposure or system maintenance, then fly to different atmospheric regions when conditions permitted or objectives required. The buoyancy provides a baseline suspension that requires no energy to maintain. The wings provide mobility that buoyancy alone cannot achieve. This flexibility would allow crews or autonomous systems to optimize their environment continuously, rather than accepting whatever conditions existed at a fixed location. The mobile platform becomes an active participant in its own survival rather than a passive structure enduring chemical assault. It can flee from adverse conditions. It can seek favorable environments. It can respond to changing circumstances rather than simply waiting for circumstances to destroy it. The psychological appeal of this active stance is substantial, suggesting mastery over the hostile environment rather than mere endurance of its attacks. The robotic-first approach extends this mobility concept even further by removing human limitations from the equation entirely. Instead of sending humans to Venus immediately where they would face all the challenges of survival in a corrosive atmosphere, proponents suggest deploying fleets of autonomous aircraft and floating platforms to establish infrastructure before crewed missions arrive. These robotic precursors could map atmospheric conditions across the entire planet, identify favorable regions for future human operations, pre-position supplies and equipment at strategic locations, and test materials and systems under actual Venusian conditions for extended durations. By the time humans eventually arrived, the robots would have created a network of support facilities distributed throughout the atmosphere. Landing zones would be characterized and marked. Supply depots would be established and stocked. Communication relays would be positioned for continuous contact. Emergency shelters would be deployed at regular intervals along potential travel routes. The infrastructure that humans need to survive would already exist, built by machines that could be sacrificed without moral cost if conditions proved more hostile than expected. This approach draws inspiration from successful Mars exploration strategies that have been refined over decades of actual operations. Robotic missions beginning with Viking in 1976 and continuing through Curiosity and Perseverance have systematically mapped Martian terrain with resolution sufficient for landing site selection. They have characterized atmospheric conditions through all seasons and weather patterns. They have identified water ice deposits that could supply future human missions. They have tested technologies required for human survival, including oxygen generation from atmospheric carbon dioxide. The resulting knowledge base accumulated over nearly 50 years dramatically reduces risk for eventual crewed missions that can build on robotic pathfinding. A similar robotic campaign for Venus could provide comparable benefits while avoiding the immediate need to solve human survival challenges that may prove impossible with current technology. Robots can accept risks that would be unconscionable for human crews. Robots can operate for extended periods without the consumables that human metabolism demands. Robots can be built in quantity and deployed in waves that establish redundancy against individual failures. The robotic approach separates the challenge of exploring Venus from the challenge of keeping humans alive on Venus, potentially enabling the former even if the latter proves permanently impossible. Autonomous systems also seem to solve the maintenance problem that plagues stationary habitats through a conceptually different approach. When a robotic platform degrades beyond repair due to corrosion or mechanical failure, it can simply be abandoned while replacement units arrive from Earth on subsequent missions. No human lives depend on any individual machine continuing to function. Failures become acceptable losses absorbed into mission planning, rather than fatal disasters requiring emergency response. The mathematics of reliability changes fundamentally when you remove human occupants from the equation. A fleet of expendable robots might accomplish scientific and infrastructure objectives that no single crewed habitat could achieve, because the fleet can absorb losses that would terminate crewed operations. The concept attracted enough serious interest that NASA funded preliminary studies examining atmospheric drone operations on Venus as potential near-term missions. Engineers at various NASA centers and contractor facilities designed aircraft capable of deploying from entry vehicles during atmospheric descent and transitioning to powered flight within the cloud layer. These designs specified aircraft capable of flying for days or weeks through the cloud layer, while conducting scientific observations and testing technologies for future missions. Solar-powered variants using high-efficiency photovoltaic cells could potentially operate for months if materials degradation issues could be managed within acceptable bounds. The technical challenges seemed formidable but not impossible given sufficient development investment. These studies produced detailed conceptual designs for Venus atmospheric aircraft. One prominent concept specified an aircraft with approximately 11-meter wingspan, carrying approximately 45 kilograms of scientific payload, while generating approximately 300 watts of continuous power from solar panels. The aircraft would deploy from an entry capsule at approximately 65 kilometers altitude, unfold its wings during descent, and achieve powered flight before reaching the corrosive cloud layer. It would then operate for a target mission duration measured in weeks to months, conducting atmospheric measurements and imaging while demonstrating technologies applicable to future missions of greater ambition. But deeper analysis reveals why mobility and robotics fail to solve the underlying problems of Venus habitation despite their intuitive appeal. The apparent solutions create new categories of difficulty that ultimately prove even more intractable than the corrosion challenge they purport to address. The physics of atmospheric operations imposes constraints that no amount of clever engineering can circumvent. The limitations of autonomous systems create failure modes that no amount of artificial intelligence development can eliminate, given foreseeable technology trajectories. Consider first the energy requirements for continuous motion through an atmosphere that never stops trying to destroy your vehicle. Maintaining altitude in a corrosive atmosphere requires constant propulsion or continuous buoyancy adjustment, because atmospheric conditions vary unpredictably with time and location. The winds that theoretically provide free horizontal transport also create turbulence and shear forces that demand active stabilization and course correction. Unlike ocean sailing, where ships can heave to under minimal sail and wait out storms in relative safety, atmospheric vehicles must continuously fight to maintain their position in three-dimensional space, because stopping means falling. The Venusian atmosphere is not the smooth, laminar medium that simplified calculations assume. Real atmospheric conditions include vertical wind speeds reaching tens of meters per second during convective events that transport heat from lower altitudes towards space. Horizontal wind shear between altitude layers creates forces that can tear apart flexible structures, attempting to transition between wind regimes. Turbulence within cloud formations, generates unpredictable accelerations that stress mechanical components in every direction simultaneously. The atmosphere actively attacks vehicles through dynamic forces as well as chemical corrosion. Solar power seems abundant in the Venusian sky given the planet's proximity to the Sun, but generating usable energy requires solar panels that face the same environmental challenges affecting other structures. Acid aerosols coat panel surfaces continuously, reducing light transmission and power generation efficiency over time. Each droplet that lands on a panel surface creates a tiny lens that concentrates sunlight onto the underlying photovoltaic material, while also depositing corrosive residue. Protective coatings that might shield panels from this contamination degrade under continuous acid exposure, just as structural coatings degrade. Even panels made from intrinsically corrosion-resistant materials experience performance decline as their optical properties change from surface etching and contamination accumulation. The power generation systems that are supposed to enable extended operations decay along the same timeline as the structures they support, creating a race condition that mobility cannot win. A platform needs power to move. Moving requires power systems. Power systems degrade in the environment that moving is supposed to escape. The degradation rate may be slightly lower for a moving platform than for a stationary one, but the degradation continues regardless of motion. Eventually the power systems fail, and when they fail, the platform can no longer move, and then stationary corrosion finishes what mobile operations delayed. Energy storage presents additional challenges beyond power generation that further constrain mobile operations. Batteries degrade in corrosive environments through mechanisms that attack both their chemical contents and their structural housings. Lithium-ion batteries, the current state-of-the-art for aerospace energy storage, contain flammable electrolytes that become increasingly dangerous as containment seals degrade. Fuel cells require consumable hydrogen and oxygen that must be transported from Earth at enormous cost or generated locally using equipment subject to corrosion. Regenerative systems that might recharge batteries or regenerate fuel cell reactants demand materials and equipment subject to the same acid attack, threatening everything else. Every component of the energy system operates under the same degradation constraints as primary structures. A mobile platform cannot escape the corrosion problem by moving through the atmosphere. It merely transfers the problem from structural materials to propulsion and power systems while adding new failure modes related to the stress of continuous operation. The wear and tear of constant motion accelerates mechanical degradation that would occur more slowly in stationary structures. Bearings wear, seals fatigue, control surfaces flutter. The platform destroys itself through operation even as the environment destroys it through chemistry. The station-keeping challenge becomes brutally apparent when examining the actual atmospheric conditions that mobile platforms would face rather than idealized smooth flow assumptions. Fighting vertical winds and horizontal shear requires power measured in kilowatts for small drones and megawatts for crewed vessels of practical size. The power requirement scales with vehicle mass and atmospheric turbulence intensity, both of which are substantial for any platform capable of supporting meaningful payload capacity. Generating such power continuously from solar panels requires surface areas of hundreds or thousands of square meters depending on vehicle size and operational requirements. Panels of this size create aerodynamic drag that increases power requirements further, establishing a feedback loop that drives system requirements upward. Larger panels mean more drag. More drag means more power needed for flight. More power means larger panels. The energy budget spirals upward until the platform requires more power to maintain position than any feasible generation system can provide within mass constraints imposed by aerodynamic performance requirements. Some proposals suggest using the atmospheric winds for passive transportation, accepting whatever path the superrotation circulation pattern dictates, rather than fighting to maintain specific positions or courses. This approach minimizes energy requirements by eliminating active station keeping entirely. The platform simply drifts with the wind, going wherever atmospheric circulation carries it, conserving power for only the most essential systems. But passive flight sacrifices control over environmental conditions that active flight was supposed to provide. The platform goes wherever the wind takes it, including through regions of maximum acid concentration that active maneuvering could theoretically avoid. The atmospheric circulation that provides free transportation does not route around the worst corrosive zones. It routes through them, because those zones exist where atmospheric dynamics concentrate acidic compounds. The reduced energy requirement of passive drift comes at the cost of increased corrosive exposure that accelerates the degradation passive operation was supposed to prevent. The mathematics cannot be reconciled through any combination of active and passive operational modes. Active station keeping requires power systems that degrade too quickly to sustain extended operations. Passive drifting exposes platforms to corrosion rates that destroy structures too quickly for mission objectives to be achieved. There is no middle ground where energy budgets balance against material lifetimes to enable sustainable operations. The physics demands compromises in both directions simultaneously, and both directions lead toward failure. The platform must either exhaust itself fighting the atmosphere or surrender itself to atmospheric conditions that guarantee its destruction. Robotic systems face their own category of fundamental limitation that mobility cannot address: the requirement for autonomous maintenance without human intervention. Any machine operating in a corrosive environment will eventually require repair regardless of how it moves or where it goes. Components fail through wear, corrosion, fatigue, and random defects that escape quality control. Connections loosen under vibration. Seals degrade under chemical attack. Electronic systems experience component failures that accumulate over time. Even the most robust designs ever conceived incorporate parts that wear out under operational stresses eventually. Human technicians can diagnose problems through observation and reasoning. They can improvise solutions using available materials in ways that designers never anticipated. They can perform repairs that extend operational lifetimes indefinitely, because human intelligence adapts to novel situations. The entire history of space exploration includes countless examples of astronauts and ground controllers devising creative solutions to unexpected problems that would have ended missions if robots had been operating alone. Apollo 13 survived because human creativity could respond to circumstances no one had planned for. Robots cannot replicate this adaptive capability. Modern autonomous systems excel at repetitive tasks, with well-defined parameters operating within thoroughly characterized environments. Manufacturing robots perform identical welding operations millions of times with superhuman precision. Autonomous vehicles navigate familiar road networks using sensor data that matches training datasets. Scientific instruments execute programmed measurement sequences without human intervention. These successes demonstrate that robots can perform known tasks in known environments reliably. But autonomous systems struggle fundamentally with novel situations, requiring creative problem-solving in environments that differ from training conditions. A robot can be programmed to replace a standard component using a standard procedure when failure modes match diagnostic patterns in its database. It cannot diagnose an unexpected failure that manifests through symptoms outside its programming. It cannot identify an improvised repair using available materials recombined in novel ways. It cannot execute a solution that requires physical manipulation beyond its designed capabilities. The gap between routine maintenance procedures and actual repair of unexpected failures represents a fundamental limitation that current artificial intelligence cannot bridge. This limitation becomes critical when operating 38 million kilometers from Earth at minimum approach distance, far beyond any possibility of direct human intervention. Communication delays between Earth and Venus range from approximately 2.5 minutes at closest approach to 14 minutes at maximum separation. Round-trip communication for a simple question and answer takes 5 to 28 minutes depending on orbital geometry. Complex troubleshooting involving multiple exchanges of diagnostic data and proposed solutions stretches to hours or days, even under optimal conditions. A robotic platform experiencing an unexpected malfunction cannot wait hours for ground controllers on Earth to analyze telemetry, develop repair procedures, test those procedures in simulators, and transmit instructions back to Venus. In a corrosive atmosphere with active degradation proceeding continuously, hours of delay can mean the difference between recoverable damage that might be patched and total loss that cannot be reversed. The communication latency that makes Mars robotic exploration challenging despite impressive successes makes Venus robotic operations nearly impossible for systems requiring Earth-based control to handle anomalies. The problem is not merely inconvenience but fundamental mission architecture. Earth-controlled robots can only respond to situations that allow time for communication round trips. Any failure that progresses faster than communication allows cannot be addressed before it becomes catastrophic. Venus atmospheric conditions create exactly such rapid progression failures as corrosion undermines structural integrity or power systems in timeframes shorter than Earth control loops can close. Autonomous artificial intelligence capable of independent problem-solving might theoretically address this communication limitation by enabling robots to respond to novel situations without waiting for Earth-based guidance. Artificial intelligence research has produced impressive results in recent years, from game-playing systems that defeat human champions to language models that generate coherent text on any topic. Perhaps sufficiently advanced AI could enable Venus robots to diagnose and repair unexpected failures independently. But current AI systems lack the general reasoning capability required for novel repair scenarios in unexplored environments. Machine learning works extraordinarily well for pattern recognition in domains with extensive training data that characterizes the full range of situations the system will encounter. Venus atmospheric operations provide no training data because no such operations have ever occurred. Every mission would operate in conditions never before encountered, facing failures never before diagnosed, requiring repairs never before attempted. No AI system can be trained for situations that have never occurred and cannot be simulated with confidence because the environment remains insufficiently characterized. The robotic fleet concept also faces mathematical challenges of scale and replacement that render it economically and logistically impossible, even if technical challenges could somehow be overcome. Each unit that fails must be replaced by a new unit launched from Earth to maintain fleet capability. Launch costs, even with modern reusable rockets that have dramatically reduced per kilogram expenses, measure tens of millions of dollars per mission at minimum. A Venus mission carrying meaningful payload mass costs hundreds of millions of dollars for launch alone, before considering spacecraft development, operations, and all other mission expenses. A fleet of dozens or hundreds of platforms requiring replacement every 1 to 2 years demands a launch cadence and budget that no space program has ever sustained for any destination. Consider what maintaining such a fleet would require in practical terms. Manufacturing replacement units requires factories on Earth, producing specialized aerospace hardware at rates matching failure rates on Venus, meaning continuous production of dozens of spacecraft annually. Testing and integration requires facilities processing each spacecraft through qualification procedures that take months per unit. Launch operations require rockets departing for Venus every few weeks, during optimal transfer windows that occur only every 19 months, demanding massive surge capacity, followed by extended idle periods. Recovery and refurbishment of reusable launch vehicles requires ground infrastructure supporting continuous operations at scales far beyond current capability. The entire space industrial complex would need to be restructured around Venus support at scales exceeding what currently exists globally for all space activities combined. The aerospace industry would need to grow by orders of magnitude specifically for Venus robot replacement, an investment that no economic rationale could justify given the returns available from Venus operations. Consider the logistics chain extending from factories to launch pads to Venus orbit to atmospheric deployment. Each link in this chain must operate flawlessly for decades to maintain fleet presence on Venus. Each link faces its own failure modes, from manufacturing defects to launch failures, to trajectory errors to deployment malfunctions. Reliability estimates for complex systems chains suggest that some percentage of replacement platforms would fail before reaching operational status on Venus. These losses must be factored into launch rates, further increasing the required cadence and budget. Some optimists suggest manufacturing replacement platforms on Venus itself using local atmospheric resources, thereby eliminating the Earth-to-Venus supply chain that makes robot fleet maintenance impossibly expensive. If robots could harvest atmospheric gases and process them into structural materials, electronic components, and propulsion systems, then failed units could be replaced by locally manufactured replacements at minimal Earth dependency cost. But manufacturing requires infrastructure that faces the same corrosion problems threatening everything else on Venus. Building a factory in the clouds demands first solving the habitat problem that manufacturing is supposed to address by providing local production capability. You cannot bootstrap industrial capability when your bootstrap facility dissolves within months of deployment. The factory needs protection from acid that no known protection can provide for the years required to establish and operate manufacturing systems. You cannot build robots to replace corroded robots using manufacturing equipment that corrodes faster than it can produce replacements. The chicken and egg problem is fundamental and inescapable. Sustainable presence requires local manufacturing. Local manufacturing requires sustainable presence to protect manufacturing facilities. Neither can exist without the other, and neither can be established first because establishing either one requires the other to already exist. The bootstrap sequence has no valid starting point. The robotic-first strategy ultimately fails because robots cannot accomplish the tasks assigned to them within the constraints imposed by Venus atmospheric conditions. They cannot maintain themselves without human intervention that communication delays prevent. They cannot operate independently across those communication delays because AI systems cannot handle novel failure scenarios that Venus operations inevitably generate. They cannot be replaced at rates matching their failure rates because the logistics chain required exceeds any plausible investment scale. They cannot establish infrastructure that humans could later occupy because any infrastructure they build degrades faster than it can be expanded or maintained to useful completion. Mobile platforms fail because mobility does not escape corrosion, but merely adds propulsion and navigation challenges to existing materials, challenges that remain unsolved. The energy required to maintain motion accelerates system degradation rather than preventing it, because power systems face the same corrosive attack as structures. Movement through the atmosphere guarantees exposure to corrosive conditions rather than avoiding them because the atmosphere contains acid throughout the altitude band where operations are possible. There is no trajectory through Venusian clouds that avoids the sulfuric acid pervading them, because the acid is everywhere. Flight is possible. The dream of sailing ships drifting through golden clouds dissolves like the ships themselves would dissolve. The vision of robot armadas preparing the way for human pioneers fades as each robot succumbs to conditions that spare nothing. Venus does not merely defeat attempts at occupation, it defeats attempts at preparation for occupation. It defeats attempts at exploration that might inform future occupation attempts. Every strategy that seems to solve one problem reveals worse problems hidden beneath the apparent solution. These cascading failures suggest a fundamentally different approach that abandons the goal of sustained presence entirely. If permanent habitation proves impossible regardless of platform mobility or autonomy, perhaps humans should simply visit Venus briefly and return before conditions destroy their equipment. Perhaps the answer is not habitation but exploration in the purest sense. Short missions that accept temporary presence without attempting long-term survival that conditions prohibit. This approach has worked for every other hostile environment humans have explored, from deep ocean trenches to volcanic calderas to polar ice caps. Perhaps Venus simply requires the same acceptance of limits that enabled exploration of terrestrial extremes. Go, observe, and leave before the environment claims you. If permanent habitation fails because corrosion destroys structures faster than they can be maintained, and robotic infrastructure cannot be established because autonomous systems cannot repair themselves across communication delays, perhaps the solution is accepting Venus as a destination for visits rather than settlement. Short-term crewed missions lasting weeks or months might accomplish significant scientific objectives while avoiding the material's degradation that defeats longer duration presence. Astronauts would arrive, conduct research, gather samples, and depart before corrosion destroyed their vehicles beyond safe operational margins. This exploration-focused approach has succeeded in every other hostile environment humans have ever entered. The intuition seems sound. Humans have explored deep ocean trenches through brief submersible dives rather than permanent underwater residence. Scientists have studied volcanic calderas through quick expeditions rather than building homes on lava flows. Researchers have investigated Antarctic conditions through seasonal stations rather than year-round occupation in the harshest regions. The pattern repeats across every extreme environment Earth offers. Go, observe, document, return. Perhaps Venus simply requires the same acceptance of limits that enabled exploration of terrestrial extremes, rather than the permanent occupation that those extremes prohibit. The concept draws from well-established precedents in human spaceflight that demonstrate temporary presence can achieve substantial objectives. Apollo missions to the Moon lasted days, not years, yet revolutionized human understanding of lunar geology and our solar system's formation. Skylab hosted crews for up to 84 days, proving that humans could live and work in space for extended periods. International Space Station expeditions typically span 6 months before crew rotation, conducting research that could not be performed on Earth, despite the obvious impossibility of permanent orbital residence without continuous resupply. Even Mars mission architectures being developed today assume stays of approximately 18 months followed by return to Earth rather than one-way colonization. The idea that humans must permanently occupy new environments before benefiting from them contradicts how exploration actually works in practice. Perhaps Venus simply requires the same temporary approach applied to a more challenging destination with appropriately reduced ambitions. Instead of cloud cities housing thousands, perhaps cloud vessels carrying 4 astronauts for 30 days. Instead of permanent infrastructure, perhaps disposable habitats that complete their mission and are abandoned to atmospheric destruction after crew extraction. The goals shift from colonization to exploration, from presence to visitation, from permanent occupation to scientific expeditions. This reframing seems to solve fundamental problems that defeat permanent presence by simply accepting that permanent presence is impossible. NASA's HAVOC study, discussed earlier as the most thorough engineering analysis of Venus atmospheric operations, explicitly adopted this temporary presence framework. Rather than attempting to solve the corrosion problem that defeats permanent habitation, the study proposed accepting material degradation as inevitable, while limiting mission duration to 30 days, brief enough that crews would depart before structural integrity declined beyond acceptable safety margins. The visit but do not stay philosophy seemed to solve the fundamental problem defeating permanent presence by acknowledging that problem rather than pretending it could be overcome. Mission architectures for short-duration Venus exploration appear technically feasible when examined against current aerospace capabilities and reasonable near-term development. Aerocapture into Venus orbit, where spacecraft use atmospheric drag to slow down rather than rocket propulsion, requires less total propellant than Mars orbital insertion through rocket braking alone. The technique has been studied extensively and could be developed with sufficient investment. Atmospheric entry and deployment of floating habitats uses technologies derived from terrestrial balloon systems that have been refined over more than a century of development. High-altitude scientific balloons routinely operate at altitudes comparable to Venus cloud layer pressure for extended missions on Earth. Solar power generation at Venus cloud-top altitudes exceeds what Mars missions receive by substantial margins due to Venus's proximity to the Sun. Photovoltaic systems proven in other space applications could be adapted for Venus operations. Communication with Earth operates in near real time compared to Mars delays, enabling ground support that Mars missions cannot receive. Every major technical element required for Venus atmospheric missions exists in some form or can be developed from current capabilities through engineering refinement rather than fundamental breakthroughs. The scientific return from even brief Venus atmospheric missions could be substantial enough to justify significant investment. No human has ever directly observed conditions in another planet's atmosphere from within that atmosphere. Robotic probes have provided limited data during their short operational lives in Venusian clouds, but those probes could carry only the instruments their designers anticipated would be useful. Human observers could conduct experiments that respond to unexpected discoveries in real time. They could investigate anomalies that robotic programming would overlook. They could gather samples selected based on observations made during the mission, rather than predetermined sampling protocols. A 30-day mission might answer questions that robotic probes have struggled to address for decades. The mysterious ultraviolet absorber in Venus's upper atmosphere remains unidentified despite numerous observations. The possibility of microbial life in the cloud layer, suggested by anomalous chemical signatures, cannot be definitively assessed by robotic instruments alone. The dynamics of the superrotation phenomenon that drives upper atmospheric circulation faster than the planet rotates remain incompletely understood. Human investigators on site could pursue these questions with flexibility that robotic missions cannot match. Proponents argue that brief visits could eventually enable longer presence through iterative learning that systematically reduces uncertainty. Each mission would test materials under actual Venus conditions rather than laboratory simulations. Each mission would refine operational procedures based on experience rather than analysis alone. Each mission would gather data informing future efforts through direct observation of degradation mechanisms and failure modes. Eventually, accumulated knowledge from a series of short missions might identify solutions to the challenges defeating permanent habitation that no amount of theoretical analysis could discover. The short-term exploration strategy becomes a stepping stone toward long-term goals rather than an admission that those goals are permanently impossible. This framework sounds reasonable until you examine what happens to human bodies during Venus missions. The framework focuses on materials and equipment, while treating the crew as payload that simply needs to be kept alive during transit and operations. But humans are not payload. Human bodies are complex biological systems that respond to spaceflight environments in ways that accumulate damage regardless of mission success. The physiological effects of spaceflight combined with Venus atmospheric residence create health consequences more severe than any previous human space mission, even those of similar or shorter duration to the transit phases alone. The visit that seems brief by mission planning standards proves devastating by human biological standards that mission planners cannot negotiate with or engineer around. Begin with the radiation environment that human bodies would experience throughout a Venus mission profile. Venus lacks the global magnetic field that protects Earth from solar energetic particles and galactic cosmic rays. Earth's magnetosphere deflects most charged particles that would otherwise bombard the surface, creating a protective bubble that extends thousands of kilometers into space. Venus has no such shield. Its negligible magnetic field provides no meaningful protection against the radiation that pervades interplanetary space. While the dense Venusian atmosphere provides some shielding at cloud layer altitudes through simple mass absorption, that shielding remains far less effective than Earth's combined magnetic and atmospheric protection. Cloud layer altitudes receive significantly higher radiation doses than Earth's surface, comparable to high-altitude aircraft operations but sustained for weeks rather than hours. Astronauts floating in Venusian clouds would accumulate radiation exposure substantially higher than what terrestrial populations experience, adding to the exposure accumulated during transit through interplanetary space where no planetary protection exists at all. Radiation damage accumulates throughout a mission with no minimum safe dose below which effects disappear. Even brief exposures contribute to lifetime cancer risk through DNA damage that may not manifest as disease for years or decades after exposure. Current radiation protection standards for astronauts allow higher doses than terrestrial workers face, acknowledging that space operations require accepting elevated risk, but those standards still impose limits that Venus missions would approach or exceed. The transit from Earth to Venus requires approximately 4 months using current chemical propulsion technology and optimal trajectory design. During this outbound journey, crews would travel through interplanetary space exposed to continuous cosmic radiation and intermittent solar particle events. Solar flares can produce intense radiation bursts that deliver potentially lethal doses within hours if crews cannot shelter behind adequate shielding mass. Interplanetary vehicles must either carry massive shielding that increases launch costs enormously, or accept that crew radiation exposure will be substantial. The outbound transit exposure, followed by 30 days in the Venusian atmosphere, where shielding is imperfect, followed by an equivalent return transit, adds up to 9 months of elevated radiation dose. This total exposure rivals the worst-case scenarios calculated for Mars missions while providing only 30 days of actual Venus science operations. The radiation cost-benefit ratio is brutally unfavorable compared to any other crewed destination under serious consideration. Current NASA guidelines limit astronaut radiation exposure based on age and sex to keep lifetime cancer mortality risk below 3% above baseline. Career dose limits range from approximately 180 to 400 millisieverts, depending on individual factors. A Venus round-trip mission with minimal shielding could deliver 250 to 400 millisieverts or more, depending on solar activity levels during the mission. A single Venus mission could consume most or all of an astronaut's career dose allowance, preventing participation in any future missions. The round-trip duration imposes cardiovascular and musculoskeletal stress that cannot be eliminated through mission design choices. Zero-gravity conditions during the 8-month transit cause bone density loss, muscle atrophy, and cardiovascular deconditioning regardless of exercise countermeasures that crews perform religiously. Current International Space Station protocols, including 2 hours of daily exercise on specialized equipment, reduce but do not prevent these effects over similar timescales. The adaptations that make human bodies efficient on Earth become liabilities in weightlessness. Venus atmospheric residence does not solve the microgravity deconditioning problem, despite the planet's near-Earth normal gravity. While Venusian gravitational conditions approach terrestrial norms, habitat designs optimized for buoyancy and mass constraints cannot provide the exercise equipment and living space required for effective physiological countermeasures. A floating habitat must minimize mass to maintain positive buoyancy margin. Exercise equipment including treadmills with restraint systems, resistance machines with cable and pulley mechanisms, and stationary bicycles with stabilization systems requires mass that directly reduces payload capacity and operational margins. Astronauts would spend 30 days in gravitational conditions better than zero gravity, but inadequate for maintaining Earth normal physiology that has already deteriorated during the outbound transit. The brief surface equivalent gravity period would be sandwiched between extended zero-gravity transits, where deconditioning would proceed largely unchecked by inadequate vehicle exercise facilities. The 30-day Venus residence cannot reverse months of accumulated physiological decline, and cannot prevent equivalent decline during the return journey. Bone density loss during spaceflight occurs at rates of approximately 1 to 2% per month in weight-bearing bones of the legs, hips, and spine. This rate substantially exceeds postmenopausal osteoporosis, the most rapid bone loss that occurs naturally on Earth. An 8-month round trip with inadequate countermeasures could result in 15 to 20% density reduction in critical skeletal structures. Some astronauts have returned from 6-month missions with bone density measurements equivalent to elderly populations. Recovery after return to Earth requires months of rehabilitation, including progressive weight-bearing exercise and careful monitoring for fracture risk. Some density loss proves permanent despite extensive recovery efforts, increasing lifetime fracture risk that remains elevated years after the mission ends. These consequences follow from the transit phases alone, before considering any Venus-specific effects on physiology that might compound the damage. Cardiovascular changes during spaceflight include fluid redistribution from lower body to upper body, cardiac muscle atrophy from reduced workload in weightlessness, and blood vessel remodeling as circulatory systems adapt to conditions that will not persist after landing. The heart shrinks measurably during extended spaceflight. Blood volume decreases as the body perceives excess fluid in the upper body and eliminates what it incorrectly interprets as surplus. Astronauts returning from 6-month missions frequently experience orthostatic intolerance upon return to gravity. They cannot maintain adequate blood pressure when standing upright because cardiovascular reflexes have adapted to weightlessness, where standing upright does not exist. Some require assistance walking after landing. Some experience fainting episodes for days after return. Longer missions exacerbate these effects because adaptation to weightlessness deepens over time, while readaptation to gravity does not become easier. Venus mission transits lasting 4 months each way fall at the upper end of current human spaceflight experience aboard the International Space Station. The physiological effects observed after 6-month missions represent the best available preview of what Venus crews would experience. But Venus crews would face 8 total months of transit, rather than 6 total months of residence. The comparison is not exact, but suggests that Venus mission health consequences would exceed current operational experience substantially. Vision changes represent a more recently recognized spaceflight hazard that has generated significant concern within the aerospace medical community. Approximately 70% of astronauts on long-duration missions experience spaceflight-associated neuroocular syndrome, characterized by changes in visual acuity, optic disc swelling, and globe flattening. The condition appears to result from increased intracranial pressure in microgravity when fluid redistribution toward the head persists without relief. Some vision changes persist permanently after return to Earth, leaving astronauts with degraded eyesight that corrective lenses can only partially address. The mechanism is not fully understood despite intensive research, and no effective countermeasure exists that has been proven in operational spaceflight. Some researchers suggest that the condition may worsen with repeated missions or longer missions, potentially creating cumulative damage that limits astronaut career duration regardless of radiation exposure. Venus mission durations fall squarely within the range where vision changes occur, with high probability based on International Space Station experience. Crews would likely experience some degree of visual impairment during the mission that might compromise their ability to perform precision tasks. The impairment might persist after return, potentially affecting career prospects and quality of life permanently. The psychological burden of Venus missions adds another dimension of health impact that cannot be quantified as precisely as radiation dose or bone density loss. Astronauts would spend 8 months confined in spacecraft volumes comparable to a large recreational vehicle, sharing that space continuously with a handful of companions from whom they cannot escape. The interpersonal dynamics that seem manageable during training on Earth become increasingly strained as mission duration extends and novelty fades into grinding routine. The 30-day Venus atmospheric residence would provide the mission's only break from transit monotony, but that break would bring its own psychological stresses unique to Venus operations. Crews would spend their time floating in an alien atmosphere, knowing that their vehicle is slowly dissolving around them despite every protective measure engineers could devise. They would perform their scientific tasks while monitoring corrosion sensors that would inevitably show progressive degradation that cannot be stopped. They would sleep in habitats that would be measurably weaker when they woke than when they slept. The 8-month return transit would follow this psychologically demanding experience with renewed confinement, now colored by uncertainty about whether damage accumulated during Venus operations would cause catastrophic failure before reaching Earth. Every creak and vibration would prompt questions about structural integrity. Every anomalous sensor reading would raise fears about system failure. The stress of this mission profile exceeds what astronauts on previous missions have experienced because previous missions did not include extended residence in actively corrosive environments. Isolation and confinement studies conducted to support Mars mission planning reveal that psychological breakdown becomes increasingly likely as mission duration and environmental hostility increase. Participants in Mars mission analog studies lasting months have experienced anxiety, depression, interpersonal conflict, and withdrawal from engagement with mission tasks. These effects occurred despite participants' knowledge that they could abort the simulation at any time and return to normal life outside the analog habitat. Actual Venus missions would offer no abort options once atmospheric entry commenced. Once committed to Venus atmospheric operations, crews would have no alternative but completing the mission profile, regardless of psychological state or interpersonal dysfunction. Emergency evacuation would require ascending to orbit, rendezvousing with the transit vehicle, and completing the 4-month return journey. The timeline for evacuation would measure weeks to months rather than minutes to hours. Psychological emergencies would need to be managed in place rather than terminated through evacuation. The cumulative health burden across radiation exposure, cardiovascular deconditioning, bone density loss, vision changes, and psychological stress makes Venus missions more physiologically costly than Mars missions of similar total duration. Mars missions at least offer surface gravity during the stay period, potentially enabling better countermeasures against cardiovascular and musculoskeletal deconditioning through proper exercise regimens. Mars' surface radiation is lower than interplanetary space because the planet's mass provides shielding. Mars offers in situ resources including water ice and atmospheric gases that could support longer stays with reduced dependence on Earth-supplied consumables. Venus offers none of these compensating advantages while imposing transit burdens comparable to Mars missions. The destination provides no resources useful for crew support. The atmospheric environment prevents effective exercise countermeasures due to habitat mass constraints. The radiation environment provides less protection than Mars surface operations. The psychological environment includes unique stressors related to corrosion awareness that Mars missions would not face. Every comparative factor favors Mars over Venus for human health outcomes. Beyond individual crew health considerations, the logistics of Venus missions create barriers that no current or planned space infrastructure can overcome, regardless of funding levels or political commitment. Each mission requires transporting not just crew and scientific equipment, but all consumables needed for a 9-month journey and 30-day surface operation. Every kilogram of food must be launched from Earth. Every liter of water must be launched from Earth. Every breath of oxygen must be launched from Earth. None of these consumables can be obtained at Venus. None can be recycled with perfect efficiency. All must be carried from departure to return. Current estimates for crewed Mars missions budget approximately 1,000 kilograms of consumables per crew member for comparable mission durations. This estimate includes food, water, oxygen, carbon dioxide scrubbing chemicals, medical supplies, personal hygiene items, and contingency reserves. The estimate assumes partial recycling of water and atmosphere that reduces but does not eliminate resupply requirements. A 4-person Venus crew would require 4,000 kilograms of life support supplies at minimum, using Mars mission assumptions that may be optimistic for Venus conditions. Add habitat mass, including structural elements, life support equipment, power generation systems, and scientific instruments. Add entry vehicle mass required to survive atmospheric entry and deploy the habitat safely. Add ascent vehicle mass required to return crew to orbit after surface operations. Add propellant for orbital operations, including rendezvous and docking maneuvers. Add transit vehicle mass for the 8-month round trip. The total mission mass approaches what the largest rockets ever built could barely deliver to Venus transfer orbit, and exceeds what current operational rockets can deliver by substantial margins. The Space Launch System, the most powerful rocket currently operational, can deliver approximately 27 metric tons to translunar injection in its current configuration, with planned upgrades potentially reaching 46 metric tons. Venus missions would require comparable or greater capability depending on specific trajectory design and mission architecture choices. The total mass required for a crewed Venus mission would require multiple Space Launch System flights, followed by complex orbital assembly operations before departure from Earth vicinity. Multiple launches and orbital assembly might reduce individual launch requirements below what any single rocket could deliver, but this approach adds complexity, risk, and cost that scale faster than mission capability increases. Each launch creates opportunities for failure. Each orbital assembly operation requires precision docking in conditions where mistakes cannot be corrected easily. Each additional mission element requires development, testing, and integration that multiplies program cost and schedule risk. The infrastructure required for regular Venus missions does not currently exist. Building that infrastructure would require investment exceeding what any space program has ever received for any purpose. The commitment would need to span decades of sustained funding through multiple political administrations and economic cycles. No comparable commitment has ever been maintained for non-military purposes in any nation's history. Consider the economics that would govern any attempt at regular crewed Venus exploration. Each mission would cost tens of billions of dollars at minimum, using the most optimistic projections that assume favorable development outcomes and efficient operations. The actual cost of novel human spaceflight programs typically exceeds initial projections by factors of 2 to 4 based on historical experience with Apollo, Space Shuttle, and Space Launch System development. 30 days of Venus atmospheric presence would cost more than entire fiscal years of current NASA budgets, even under optimistic assumptions. NASA's annual budget currently measures approximately $25 billion. A single Venus mission might cost $50 billion or more spread across a decade of development and operations. Scientific return from such missions, while potentially significant for atmospheric science and astrobiology, cannot justify expenditure at scales that would consume entire space programs for marginal additional knowledge compared to robotic alternatives. The cost-benefit mathematics makes regular crewed Venus visits economically impossible under any foreseeable funding scenario. Governments facing competing demands for healthcare, infrastructure, defense, and social programs cannot allocate tens of billions of dollars for scientific expeditions that risk crew lives for 30 days of data collection. Private entities pursuing profitable space activities cannot justify investments that provide no revenue return. Neither public nor private funding models support Venus crewed exploration at scales necessary to make it happen. Some proposals suggest reducing costs through reusable vehicles, advanced propulsion, or in-space resource utilization that transforms mission economics. But each cost reduction approach adds technical challenges on top of already formidable requirements that remain unsolved. Reusable Venus atmospheric vehicles would need to survive corrosion during descent, residence, and ascent while maintaining structural integrity for refurbishment. They would need to be serviced in Venus orbit using facilities that do not exist and would themselves require enormous investment to establish. Advanced propulsion technologies, including nuclear thermal rockets, electric propulsion systems, or more exotic concepts, remain decades from operational capability at scales relevant for crewed missions. Development timelines for new propulsion systems historically stretch longer than initial projections. Even optimistic assessments place advanced propulsion readiness for crewed interplanetary missions in the 2040 to 2050 timeframe or later. Venus offers no accessible resources for in-space utilization comparable to what water ice provides at Mars or lunar poles. Water ice can be processed into hydrogen and oxygen for propellant and life support. Mars' atmospheric carbon dioxide can be processed into oxygen and methane. Lunar regolith contains oxygen bound in mineral compounds. Venus clouds contain sulfuric acid, carbon dioxide, and nitrogen in an environment that destroys processing equipment faster than it can produce useful quantities of anything. The resource utilization strategies that might reduce Mars or lunar mission costs do not apply to Venus. The economics and logistics of human Venus exploration cannot be made to work regardless of which variables planners adjust. Health costs exceed acceptable limits that ethics boards would approve for human subjects research. Financial costs exceed available resources that any plausible funding source would provide. Return on investment fails to justify expenditure when robotic alternatives could answer most scientific questions at small fractions of crewed mission costs. The brief visit strategy that works for moon exploration and might eventually work for Mars does not scale to Venus conditions. The destination is simply too hostile, too demanding, and too expensive to visit repeatedly using any plausible near-term technology. These comprehensive failures of temporary presence through crewed exploration lead naturally to the most ambitious proposals of all. If we cannot survive in Venus as it currently exists because every material we possess degrades faster than we can replace it, perhaps we should change Venus itself. If the atmosphere is corrosive because of its chemical composition, perhaps we should modify that composition to something more benign. If current conditions prevent habitation regardless of mission architecture, perhaps we should transform those conditions into something that permits habitation. The grand vision of terraforming Venus has captivated scientists and dreamers for generations precisely because it bypasses all the problems that defeat lesser approaches. Why adapt to Venus when you can adapt Venus to us? Surely at sufficient scale and ambition, human ingenuity can overcome any obstacle the universe presents. If Venus defeats every attempt at habitation within current conditions, perhaps the solution is changing the conditions themselves. Terraforming the transformation of alien environments into Earth-like habitats through deliberate planetary engineering represents the ultimate expression of human technological capability applied at scales that dwarf any previous endeavor. Venus offers the most challenging terraforming target in our solar system due to its extreme atmospheric conditions, but some scientists argue it also offers the greatest potential reward. A world nearly identical to Earth in size and gravity, positioned closer to the Sun than any alternative destination, waiting to be remade into humanity's second home. The logic seems unassailable on first examination. If the atmosphere is the problem, change the atmosphere. If the temperature is lethal, reduce the temperature. If the chemistry destroys our materials, transform the chemistry into something compatible with human technology. The obstacles that defeated cloud cities, mobile platforms, and brief expeditions all stem from Venus as it currently exists. A transformed Venus would present none of these obstacles. The problem is not that humans cannot survive on Venus. The problem is that Venus has not yet been prepared for human survival. Preparation is simply a matter of sufficient effort applied over sufficient time. The concept of Venus terraforming dates to the 1960s when astronomer Carl Sagan, then a young researcher at Harvard, proposed introducing photosynthetic organisms into the Venusian atmosphere as a planetary-scale biological intervention. These engineered organisms would consume carbon dioxide and release oxygen, gradually converting the suffocating atmosphere to breathable composition, while simultaneously reducing the greenhouse effect that maintains surface temperatures hot enough to melt lead. Over time, perhaps centuries or millennia, Venus might cool enough for liquid water to condense from atmospheric vapor and pool on surfaces no longer hot enough to vaporize it instantly. Sagan's proposal captured scientific imagination precisely because it offered a path from current impossibility to future habitability through processes that, while unprecedented in scale, involve no violations of known physics. Photosynthesis works. Organisms can be engineered. Atmospheres can change composition over time. Earth's own atmosphere transformed from carbon dioxide dominance to oxygen richness through biological processes over billions of years. Perhaps human intervention could accelerate natural processes to achieve in centuries what evolution achieved in eons. Later proposals built on Sagan's biological foundation with increasing technical sophistication as understanding of Venus improved and engineering capabilities expanded. Atmospheric processing plants deployed throughout the cloud layer could accelerate chemical conversion beyond what biological systems alone could achieve. Solar-powered facilities would harvest atmospheric carbon dioxide, crack it into carbon and oxygen, sequester the carbon as solid material, and release the oxygen to gradually shift atmospheric composition. Industrial chemistry would accomplish what biology alone could not achieve quickly enough for human timescales. Orbital sunshades emerged as another terraforming approach that addressed temperature directly, rather than working through atmospheric composition changes. Positioned at the Venus-Sun Lagrange point where gravitational forces from both bodies balance to permit stable positioning, massive reflective structures could reduce solar input, reaching Venus by significant fractions. Less sunlight would mean less heating. Less heating would allow temperatures to drop across the planet. Eventually, after decades or centuries of reduced solar input, surface conditions might moderate toward habitability even before atmospheric composition changed substantially. Asteroid and comet impacts could deliver materials that Venus lacks but habitability requires. Venus is remarkably dry, with atmospheric water vapor measuring only trace concentrations compared to Earth's oceans. Redirecting ice-rich bodies from the outer solar system to impact Venus could deliver water in quantities sufficient to create seas and moderate climate. Nitrogen-rich asteroids could supplement atmospheric nitrogen to create breathable gas mixtures once oxygen concentrations increase sufficiently. The solar system contains vast reservoirs of volatile materials. Terraforming would simply relocate those materials to where humans want them. Each new concept addressed limitations of earlier proposals, while demonstrating that terraforming was at least theoretically possible given sufficient resources and time. Biological approaches were too slow, so add industrial processing. Atmospheric modification alone was insufficient, so add solar radiation management. Venus lacks water, so import water from elsewhere. The terraforming literature accumulated into an impressive body of work, showing multiple pathways from current Venus to habitable Venus. Each pathway technically feasible in principle, even if challenging in practice. The most comprehensive contemporary terraforming proposals integrate multiple intervention strategies into coordinated campaigns spanning centuries. Phase 1 would deploy sunshades at the Venus-Sun Lagrange point, reducing solar input by approximately 40% to begin passive cooling. Phase 2 would establish atmospheric processing infrastructure in orbit and in the upper atmosphere, converting carbon dioxide to oxygen and solid carbon at industrial scales. Phase 3 would redirect cometary bodies to deliver water and nitrogen, as temperatures dropped sufficiently to prevent immediate loss to space. Phase 4 would seed the modified environment with engineered organisms to establish self-sustaining biological cycles. Phase 5 would manage the transition to human habitation as conditions reach survivable thresholds. The scale of these integrated proposals staggers imagination in ways that single-component approaches do not fully convey. Sunshades, capable of reducing solar input by meaningful percentages, would need to span hundreds of thousands of square kilometers of reflective surface area. The structures would exceed the largest objects humanity has ever constructed by factors of thousands. Manufacturing the reflective material alone would require industrial output exceeding current global production of comparable materials by orders of magnitude. Hydrogen importation to create water from atmospheric carbon dioxide would require redirecting comets or harvesting outer planet moon material across billions of kilometers of interplanetary space. Each comet impact would deliver perhaps a few billion tons of ice, substantial by terrestrial standards but trivial compared to Earth's ocean mass of approximately 1.4 billion tons. Creating even modest seas would require redirecting thousands of comets over extended campaigns spanning centuries of continuous effort. Atmospheric processing to convert carbon dioxide to oxygen and sequestered carbon would need to transform approximately 465,000 trillion tons of carbon dioxide, the total mass of Venus's atmosphere. Even aggressive processing scenarios propose handling only billions of tons annually, meaning complete atmospheric conversion would require hundreds of thousands of years at proposed rates. Accelerating the timeline to centuries rather than millennia would require processing infrastructure of unimaginable scale, consuming energy resources that dwarf current human civilization's total output. The resources and energy required for Venus terraforming exceed anything human civilization has ever mobilized for any purpose by factors that render historical comparisons meaningless. The Great Wall of China required perhaps 20 years of intensive effort from a substantial fraction of Chinese civilization. The Apollo program required approximately 4% of United States federal budget at peak spending for less than a decade. Venus terraforming would require equivalent commitment levels sustained for centuries to millennia, with total resource expenditure exceeding all human economic activity throughout recorded history. But proponents argue that scale alone does not indicate impossibility, it merely indicates ambition beyond current capability. Human civilization has grown exponentially in energy use and industrial capability throughout recorded history. Technologies that seemed impossibly ambitious in previous generations became routine within decades as capabilities expanded. Steam power was inconceivable before the Industrial Revolution. Nuclear energy was science fiction before the 20th century. Space travel was fantasy before the rocket age. Perhaps Venus terraforming represents the natural extension of human capability that future generations will find achievable, given sufficient motivation and resources that their expanded civilization can command. The appeal of transformed Venus is substantial enough to sustain this optimism across decades of analysis and proposals. A fully terraformed Venus would offer surface gravity, measuring approximately 90% of Earth normal, closer than any other planetary body in the solar system except Earth itself. Mars offers only 38% of Earth gravity. The Moon offers only 17%. Low gravity creates physiological challenges for long-term human residence that Venus's near-Earth gravity would entirely avoid. Surface area of a terraformed Venus would provide living space for billions of humans across continents worth of habitable land. Earth's surface area totals approximately 510 million square kilometers. Venus's surface area totals approximately 460 million square kilometers, comparable to Earth and vastly exceeding what any other terraforming target could offer. Mars has only about 145 million square kilometers of surface area. A single terraformed Venus could accommodate human population measured in billions rather than millions. Solar energy availability at Venus exceeds what Earth receives by significant margins due to Venus's closer orbit around the Sun. A civilization living on terraformed Venus would have abundant renewable energy resources for industrial processes and daily living. The proximity to Earth would enable communication and transportation on timescales dramatically shorter than for outer solar system destinations. A successfully terraformed Venus might become humanity's most valuable real estate outside Earth itself, justifying any investment required to achieve it. This vision has attracted serious scientific study from researchers across multiple disciplines who have published extensively in peer-reviewed literature. Climate scientists have modeled atmospheric evolution under various intervention scenarios, using sophisticated computational tools adapted from terrestrial climate research. Planetary geologists have characterized surface conditions and potential material resources using data from Soviet and American Venus missions. Aerospace engineers have designed conceptual space-based infrastructure required for large-scale planetary modification. The technical literature on Venus terraforming spans thousands of pages accumulated across decades of analysis by credentialed researchers at respected institutions. But this accumulated study reveals why Venus terraforming fails despite the genuine expertise applied to its analysis. The failure arises not from lack of imagination or insufficient technical sophistication, but from fundamental physical constraints that no amount of technology or resources can overcome within frameworks that matter for human purposes. The proposals are not impossible in any absolute sense. They violate no physical laws. They are impossible in practical senses that render the distinction between theoretical possibility and actual achievability meaningless. The first insurmountable barrier is energy at scales that make the word meaningless. Removing the thermal energy stored in the current Venusian atmosphere would require approximately 10 to the 27th joules, 1,000 trillion joules expressed in conventional notation. For perspective, this quantity equals total human energy consumption at current rates sustained for approximately 300 million years. The entire history of human civilization, from stone tools to nuclear reactors, has consumed less energy than Venus atmospheric cooling would require. Even optimistic projections for human energy growth over coming centuries cannot approach the sustained output necessary for active thermal extraction from Venus within any time frame compatible with project continuity. The sunshade approach reduces direct energy requirements by allowing passive cooling over time, rather than active thermal processing. The sun does the energy-intensive work of maintaining Venus's current temperature, block the sunlight, and temperatures drop without human energy input. The physics is sound, But constructing and maintaining sunshades of sufficient scale poses its own energy challenges that merely relocate rather than eliminate the fundamental constraint. Manufacturing reflective material sufficient to cover hundreds of thousands of square kilometers requires mining raw materials from asteroids or planetary bodies, processing those materials into usable forms, fabricating finished products with precise optical properties, transporting completed components to the Venus-Sun Lagrange point, and assembling them into coherent structures that maintain position and orientation for centuries. Each step demands energy input, measured in exajoules, billions of joules. The total energy invested in shade construction across a multi-century campaign would rival the thermal energy the shade is meant to reject, eliminating the efficiency advantage that made sunshades attractive compared to active cooling. Carbon dioxide sequestration creates another energy bottleneck, regardless of which approach is chosen for atmospheric modification. The Venusian atmosphere contains approximately 465,000 trillion tons of carbon dioxide that must be converted to stable non-greenhouse forms for habitable conditions to emerge. Converting carbon dioxide to solid carbon and gaseous oxygen requires energy input to break molecular bonds, approximately 393 kilojoules per mole of carbon dioxide processed. Total sequestration energy for complete atmospheric conversion measures approximately 10 to the 24th joules, still vastly exceeding any plausible energy budget, but now spread across chemical processing rather than thermal extraction. Timescales compound these energy constraints in ways that transform difficult into impossible. Even assuming unlimited resources and perfect efficiency in converting resources to terraforming outcomes, atmospheric modification would require centuries to millennia to achieve habitable conditions through any proposed mechanism. The fastest cooling scenarios in published literature involve multiple human generations of continuous effort before surface temperatures permit unprotected human presence for even limited durations. More realistic scenarios accounting for practical constraints span thousands of years timescales, measured against geological epochs rather than human history. This temporal requirement reveals the truly insurmountable barrier to Venus terraforming. No human institution has ever sustained coherent purpose for timescales that the project demands. The longest-lasting human organizations, ancient religions, continuous governments, persistent cultural traditions, measure their histories in centuries at most. The Catholic Church has existed for approximately 2,000 years, but has undergone fundamental transformations in doctrine, structure, and purpose multiple times across that span. China has maintained continuous civilization for several thousand years, but has experienced dynastic collapses, foreign conquests, and revolutionary upheavals that completely reconstituted governmental structures and societal goals. The project of Venus terraforming would need to maintain consistent direction, sustained funding, continuous technical capability, and persistent institutional memory across time spans longer than any existing human enterprise has survived in any recognizable form. The commitment cannot waver for centuries. The technical approach cannot fundamentally change once infrastructure investment begins. The political will cannot fade as generations pass, and the original motivations become historical abstractions rather than lived concerns. Consider what maintaining such a project would require in practical terms that translate theoretical timelines into institutional demands. Resource extraction and processing facilities operating continuously for hundreds of years without the economic disruptions, technological obsolescence, or political interference that have affected every long-term industrial enterprise in human history. Space-based manufacturing producing sunshade components and atmospheric processing equipment at steady rates across generations, despite the turnover of personnel, evolution of methods, and transformation of supporting economies that characterize every human endeavor on multi-decadal timescales. Transportation networks delivering materials from across the solar system without interruption despite the accidents, equipment failures, and operational challenges that affect every logistics system ever created. Communication and coordination systems maintaining coherent project management across Earth, Venus orbit, and various extraction sites despite the institutional drift that affects every organization over time. All of this sustained through technological changes that obsolete established approaches, social upheavals that redirect civilizational priorities, economic transformations that restructure resource availability, and the ordinary chaos of human civilization that has disrupted every long-term project ever attempted. History provides no examples of projects operating at scales and durations remotely approaching what Venus terraforming requires. The largest construction projects in recorded history, great walls extending thousands of kilometers, canal systems spanning continents, cathedral complexes built across centuries required decades of concentrated effort, not millennia. The most intensive technological mobilizations, the Manhattan Project developing atomic weapons, the Apollo program achieving lunar landing, represented peaks of societal effort lasting less than a single decade each, before political attention shifted elsewhere. Asking human civilization to maintain consistent effort across time spans 50 to 100 times longer than these exemplary mobilizations defies everything historical experience teaches about human institutional behavior. Civilizations rise and fall on timescales shorter than Venus terraforming requires. Technologies transform utterly across centuries in ways that invalidate earlier approaches. Social values evolve to reject priorities that earlier generations held sacrosanct. No mechanism exists for binding future generations to commitments made by ancestors whose concerns they do not share and whose methods they have superseded. The terraforming concept also assumes that Venus, once modified through whatever effort the modification required, would remain in its transformed state indefinitely without continued intervention. This assumption of stable endpoints fails catastrophically when examined against the planetary physics that would govern post-terraforming Venus. The planet lacks fundamental characteristics that enable Earth to maintain habitable conditions across geological time. Without those characteristics, any habitable state achieved through terraforming would degrade back toward current conditions unless perpetual maintenance prevented regression. Venus lacks the global magnetic field that protects Earth's atmosphere from erosion by solar wind, the continuous stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. Earth's magnetic field deflects most of these particles around the planet, preventing them from stripping away atmospheric gases through momentum transfer. Venus has no such protection. Whatever atmosphere terraforming creates would be gradually eroded by the same solar wind that has stripped Venus of whatever original atmosphere it possessed billions of years ago. The solar wind strips approximately 100 grams of atmosphere from Venus per second at current measurement rates. This might seem negligible against an atmosphere massing hundreds of thousands of trillion tons, but the loss accumulates across the geological timescales relevant to planetary habitability. A terraformed atmosphere with reduced density and different composition might experience different loss rates than the current thick carbon dioxide atmosphere, but some erosion would certainly continue at rates measured in billions of tons per millennium. Over the millions of years that habitability must persist to justify terraforming investment, losses would accumulate to significant fractions of total atmospheric mass, requiring continuous replacement from imported sources. Volcanic activity presents another stability challenge that terraforming cannot permanently resolve. Venus displays evidence of geologically recent volcanic resurfacing across significant fractions of its surface. Lava flows and volcanic constructs visible in radar imagery suggest that the planet remains volcanically active, with internal heat continuing to drive magmatic processes that release gases into the atmosphere. Carbon dioxide, sulfur dioxide, and water vapor emerge from volcanic vents as they do on Earth. But Earth's biological and chemical cycles sequester these emissions, while Venus lacks such cycling mechanisms. Whatever atmospheric composition terraforming achieves would be continuously modified by ongoing volcanic outgassing that human intervention cannot stop. The internal heat-driving volcanism will persist for billions of years regardless of surface conditions. Maintaining terraformed atmospheric composition would require processing volcanic emissions faster than they accumulate, another indefinite maintenance commitment, adding to the perpetual effort required to counter solar wind erosion. The terraformed state is not an endpoint but a temporary configuration requiring eternal vigilance to maintain. The rotation rate of Venus creates additional challenges for habitability that terraforming atmospheric conditions alone cannot address. Venus rotates so slowly that a single Venusian day lasts longer than a Venusian year, 243 Earth days for one complete rotation versus 225 Earth days for one orbital period around the Sun. This extraordinary slow rotation means that any given surface location experiences approximately 4 Earth months of continuous daylight, followed by approximately 4 Earth months of continuous darkness. Habitable conditions on a terraformed Venus would require managing these extreme day-night cycles through ongoing climate engineering that prevents temperature extremes during extended darkness and prevents overheating during extended daylight. Earth's rapid rotation distributes solar heating relatively evenly across longitudes, preventing the thermal extremes that would otherwise develop. Venus's slow rotation provides no such natural moderation. Human intervention would need to compensate perpetually for what planetary rotation accomplishes automatically on Earth. Some proposals suggest spinning up Venus to Earth-like rotation rates through mechanisms ranging from controlled asteroid impacts to atmospheric manipulation to gravitational interactions with deployed mass concentrations. The energy required for rotational modification approaches the energy required for atmospheric modification, approximately 10 to the 29th joules applied over centuries to change angular momentum by factors of 60 or more. The proposed mechanisms remain firmly in the realm of speculation, without any clear path to implementation, even in principle. Changing how fast a planet rotates is not merely difficult, it approaches the impossible given any foreseeable technology. The terraforming vision fails because it assumes human capability, without accounting for human limitations that define what capability means in practical terms. It imagines resources without accounting for the costs of obtaining and deploying those resources across the timescales involved. It proposes timelines without acknowledging the institutional fragility that has characterized every long-term human endeavor throughout recorded history. It describes endpoints without recognizing the maintenance requirements that transform endpoints into perpetual beginnings. Every element that makes the vision appealing, permanent transformation, stable results, Earth-like conditions achieved once and enjoyed forever, proves illusory upon examination against physical and institutional constraints. This brings us to a disturbing question that haunts every Venus habitation proposal examined throughout this exploration. Why do we keep proposing these ideas? Decade after decade, generation after generation, scientists and engineers revisit Venus with new proposals that seem promising on first examination until closer analysis reveals their fatal flaws. The Cloud City concept has been proposed in various forms since the 1960s. Mobile platform concepts have circulated since the 1980s. Brief expedition architectures have been studied since the 2000s. Terraforming proposals have accumulated for more than half a century. Each proposal collapses under scrutiny, yet new proposals continue emerging with authors apparently unaware of or undeterred by the failures of their predecessors. What drives this persistent optimism about a destination that analysis consistently proves impossible? Part of the answer lies in how Venus appears from Earth and the psychological power of that appearance. Our sister planet shines brilliantly in our sky, the third brightest object visible after the Sun and Moon, beautiful and seemingly close. Venus approaches Earth more closely than any other planet, creating an illusion of accessibility that other destinations do not generate. Its size and surface gravity match Earth more closely than Mars or any moon we might consider inhabiting. Its atmosphere, while hostile in its current composition, at least exists as substantial material that might be transformed, unlike the vacuum at the Moon or the thin whisper of gas at Mars. Venus seems like it should be habitable in ways that other destinations do not. and this seeming creates expectations that analysis must repeatedly disappoint. Another part of the answer reflects human reluctance to accept limits of any kind, a psychological characteristic that has served our species well throughout evolutionary and historical development. We are a species that has overcome seemingly impossible barriers throughout our existence on this planet. Oceans were once uncrossable until ships and navigation enabled transoceanic travel. Mountains were once unclimbable until equipment and techniques enabled summiting the highest peaks. The atmosphere was once unreachable until balloons and aircraft enabled flight. Space was once unthinkable until rockets enabled orbital and interplanetary missions. Each barrier fell to human ingenuity applied with sufficient determination, and we understandably assume that future barriers will fall as well if we simply try hard enough and think cleverly enough. But Venus reveals a category of barrier that differs in kind from previous challenges humanity has overcome. The obstacles to Venus habitation are not technological gaps awaiting clever solutions that the right insight will provide. They are physical constraints arising from fundamental chemistry and thermodynamics that operate identically regardless of how much cleverness we apply to circumventing them. Sulfuric acid corrodes materials because of molecular properties inherent to how sulfur, oxygen, and hydrogen atoms combine. Those properties cannot be engineered away. Energy requirements scale with mass and temperature because of thermodynamic laws that govern all physical transformations. Those laws cannot be circumvented through better technology. Timescales extend beyond human institutions because of physical speeds set by chemistry and orbital mechanics rather than policy choices. Those speeds cannot be accelerated by wishing they were faster. Recognizing these limits does not diminish human achievement or permanently constrain human ambition to boundaries we currently perceive. The universe offers countless destinations where human presence may eventually flourish through technologies and approaches we cannot currently specify, but that remain physically possible. Mars presents challenges that, while severe enough to have prevented human landing thus far, fall within conceivable technological solutions involving radiation shielding, resource extraction, and habitat construction that violate no physical laws. Outer solar system moons offer resources and conditions that patient development might eventually exploit for human benefit. Even interstellar destinations, though impossibly distant by any current technological measure, do not violate fundamental physical constraints on human survival in the way that Venus does. Venus is different from these other challenging destinations in ways that matter for how we should think about it. Venus is not a problem awaiting solution through sufficient investment of effort and ingenuity. Venus is a lesson about boundaries that exist regardless of human preferences. Some environments resist human presence, not because we have not tried hard enough or thought cleverly enough, but because the physics and chemistry of those environments are fundamentally incompatible with the physics and chemistry required for human survival. Recognizing this incompatibility is not defeat. It is wisdom that enables directing effort toward achievable goals rather than dissipating effort against immovable constraints. The story of Venus habitation proposals illustrates how human ambition can race ahead of physical reality in ways that generate decades of wasted analysis. Each proposal begins with genuine insight into some aspect of Venus conditions that might permit survival under specific circumstances. The temperature and pressure at 50 kilometers altitude really do match Earth. The physics of buoyancy in dense atmosphere really does favor floating structures. The proximity really does minimize travel and communication times. These insights are correct as far as they go. Each proposal then runs headlong into constraints that genuine insight overlooked or underestimated: corrosion rates, energy requirements, physiological costs, institutional demands, planetary physics. The pattern has repeated for 6 decades, without variation, because the underlying physics has not changed and cannot change, regardless of how many times we revisit the analysis with fresh eyes and new approaches. Perhaps future technologies will enable approaches not yet conceived that circumvent constraints visible from current vantage points. Perhaps materials science will discover compounds that resist concentrated sulfuric acid indefinitely through mechanisms we cannot currently imagine. Perhaps energy technologies will make atmospheric processing economically viable through breakthroughs that transform cost structures. Perhaps artificial intelligence will enable autonomous maintenance beyond current imagination through capabilities that emerge from continued development. Perhaps social technologies will enable multi-generational projects beyond historical precedent through institutional innovations that have no current analogues. But perhaps not. Perhaps Venus will remain what it has always been throughout human awareness of its nature, a cautionary example of how hostile the universe can be to life as we know it. Perhaps the brilliant ideas that seem to solve Venus will always collapse under examination, not because we are insufficiently clever, but because clever ideas cannot overcome physical constraints that exist independent of human wishes. Perhaps the cloud cities will never float. Perhaps the mobile platforms will never sail. Perhaps the brief expeditions will never launch. Perhaps the terraforming will never begin. The universe is vast beyond comprehension, containing more stars than grains of sand on every beach on Earth, more planets than human minds can enumerate or imagine. Among this cosmic abundance of potential destinations, Venus orbits closest to our home among the planets, while remaining utterly inaccessible to our presence through any mechanism foreseeable from current knowledge. The proximity that makes Venus seem accessible is precisely what makes its inaccessibility so poignant. We can almost reach it. We can almost survive there. We can almost make it work, but almost is not enough when physics demands certainty. We can study Venus through telescopes and orbital spacecraft. We can admire its brilliant beauty in our evening and morning sky as humans have done for all of recorded history. We can send robotic probes that survive for hours or days before the environment inevitably claims them. What we cannot do, what we may never be able to do, regardless of how technology advances, is live there. Not in its clouds where acid dissolves everything we build. Not on its surface where temperatures melt metal and pressures crush steel. Not in any form that resembles human habitation as we understand it. This conclusion feels like defeat to a species accustomed to conquering hostile environments through determination and ingenuity. But perhaps it represents something more valuable than conquest. Recognition that some destinations exceed our reach, some problems lack solutions, and some visions will remain forever unrealized regardless of effort invested in pursuing them. The universe does not owe us hospitality. Most of the cosmos is and will remain incompatible with human survival. This is not failure, but simply reality that wisdom requires accepting. Venus teaches this lesson with particular clarity because it comes so close to being habitable before failing so completely. The coincidence of Earth-like temperature and pressure at 50 kilometers altitude is genuine and remarkable. The physics of buoyancy really does favor floating structures in the dense atmosphere. The proximity really does minimize travel times and communication delays compared to more distant destinations. Everything about Venus suggests it should be accessible to human presence, and yet it is not. The clever Venus idea that sounds brilliant until you look closer turns out to be every Venus idea ever proposed. Cloud cities dissolve in acid that pervades the altitude band where they would float. Mobile platforms cannot sustain themselves against corrosion that attacks every system, enabling their mobility. Brief visits impose physiological and financial costs that exceed any plausible return. Terraforming exceeds civilizational capacity across timescales longer than human institutions persist. Each proposal collapses under the weight of constraints that no ingenuity can overcome, because those constraints arise from physics rather than insufficient effort. And perhaps that is the most important lesson Venus has, to teach a species that imagines itself capable of any achievement given sufficient determination. In a universe where human ambition perpetually strains against cosmic indifference to human preferences, wisdom lies in recognizing which barriers will fall to sustained effort and which will stand forever, regardless of how hard we push against them. Venus stands, and will continue standing, beautiful and close, and utterly beyond our reach.